So now that we have a rough idea of what a sequence is, let's go ahead and start to try to use it in some simple ways. Take a look here at example number 1. I'm going to go to a sequence that's given by this formula down here, and I want to write the first 5 terms or items in that sequence, kind of like how up above I have the first 5 numbers written down for this sequence. Well, to do this, it's not too difficult. Again, if I want the number that's in spot 1, I just have to replace n in my formula with the number 1. So a number 1 would be 1 over 1 plus 1, or 1/2. To get the second number, I would just plug in a 2. Notice that would give me the value 2/3. A3 would be plugging a 3 in for each of my values of n. That would be 3 over 4. A number 4 gets me 4 over 5, and a number 5 gets me 5 over 6. So I could write this. I can then see that the kind of list of the order, or I can then see that these numbers would create a list that has the following order. 2/3 follows the 1/2, and then I get a 3/4, then a 5/4, and then a 5/5, and it seems like this sequence would probably continue on forever since I don't have any stopping point that's specified. If I take a look at part B, I'll notice that I can do the same sort of thing. Here I want to find a number 3, a number 4, and a number 5. So notice here that this is a formula again that produces the numbers in my list, but very interestingly here, notice that the smallest value of n that I'm able to work with is actually the number 3. This shows kind of some strangeness that can occur in the way that we label these terms of the sequence. Here, a number 3 is actually the first number that comes out of this list. I'm starting from counting at 3. So notice here I can go ahead and just quickly calculate that a number 3 is going to turn into the square root of 3 minus 3, that is 0. A number 4 is going to be square root of 4 minus 3, or just 1. And a number 5, square root of 5 minus 3, just going to be square root of 2. Now, again, as I mentioned in the last video, it's possible that we could start our sequence at any number. And the most common values to start at are often going to be 1, like we did up above, or 0. For those of you who may have actually taken courses already in computer science, you know that sometimes we're accustomed to starting our counting from having a value be 0. And you're more than welcome to do that when you work with certain problems that we'll see in the next video, where I ask you to maybe create your own formula. But we're always going to assume that unless specified, like down here on part B, our lists will always start by plugging in a value of 1. Now, the lists that we've created here, we can see come from these individual formulas that were given on each of these parts. These formulas up here are what we refer to as explicit formulas. Notice that they allow us to actually jump to any spot within the entire list. Like up here, if I want to know the number in spot 100 in this list, I would get 100 over 101. Pretty easy. Same thing here. But notice down below, sometimes I can have sequences that are communicated slightly differently. Here, I want to find the first 5 terms of the following sequence, which is given recursively. Let's take a look at what that means. Notice we're already told what f number 1 and f number 2 are, which is great. We're already kind of like 2/5 of the way done. And then this formula here is going to help me determine what happens whenever n is 3 or bigger. So let's go ahead and write down what we have. F number 1 is 1, and f number 2 is 1. But to find f number 3, I have to use this formula. Notice if I replace all the n's with 3's, I'm going to get f number 2 plus f number 1. Ooh, I already have those values. That's 1 plus 1. So the third thing in my list here is a 2. Okay, so I can do the same thing to get f number 4. Using the formula, this would tell me that f number 3 plus f number 2 needed to be added together to create this value. F number 3 is a 2, I can establish that from right here, and f number 2 is a 1. Add those up, I get a 3. I can also find f5. That's going to be f4 plus f3. So that's 3 plus 2, that makes 5. So the list as I'm creating it so far goes 1, 1, 2, 3, 5, and so on. You can almost see the pattern right here from taking a look at the general formula. That is, whenever I want to get a new number in the list, I have to look at the previous two numbers and add them together. So it's probably no surprise then that the next number here in this list would be given by 8, the sum of 3 and 5. The next number would be 5 plus 8, or 13, and then 21, and so on. And this is what's known as actually the Fibonacci sequence. It's a very famous sequence. You might already be familiar with it. But what you'll notice is that when I have a sequence that's given in this kind of recursive form, things are much more difficult. Because let's suppose I wanted to find the 100th item of the Fibonacci sequence. Well, to find thing 100, I would need to know thing number 99 and thing number 98. But I don't have those yet. No big deal, though, because we can find those, right? So, like, if I want thing number 99, I just need to know thing number 98 and thing number 97. Well, that's easy. No big deal. Let's see. To find thing number 98, I just need to know thing number 97 and thing number 96. Like, oh, gosh. You can see that if I want to know a value, I have to know values that come before it. That's the idea of a recursively defined sequence. To get something new in the list, I have to know something old in the list, maybe multiple old things. But what I can see up above in what again we called explicit formulas is that I can kind of jump to any spot in the list that I want. We really like explicit formulas. And while recursive formulas are oftentimes easier to come up with when we're trying to write formulas for sequences, they're oftentimes not as good. And there are whole areas of mathematics that are focused on how can I take a recursively defined sequence and change it into something that's explicit. We're going to be dealing primarily with explicit formulas for sequences in this section, but every so often we'll come across some things that are indeed recursively defined.